So we're in section 10.3, area of regular polygons. First off, let's remember what we mean. First, what's a polygon?
Is this on the organizer?
No. So I'll tell you when you need to add information to the organizer. Most of the stuff we type. What's that?
On the back or different?
There's you'll have to take notes separately from the organizer. On the back is other parts of the graphic organizer.
Never mind.
So I'll tell you when to add information to your graphic organizer. So let's remember what a polygon is. What makes a polygon? What kind of thing is it? Something with sides? It has something to do with sides. Lots of what we do with sides. So what kind of sides? So let's back up just a second. Just a polygon. Just a polygon. What's a polygon? Sides. It has sides. Straight sides. Okay, good. Closed. It has to be closed. So a polygon is some closed figure with straight sides. So a triangle, a square, those would be polygons. What do we mean? And I think Spencer was on top of it already. What do we mean when we talk about what does regular mean? What is that telling us about the polygon? The angles and the sides are the same. Same angle measures and same side lengths. So what we're talking about in this section and really in this unit, we're talking about regular polygons. If it's irregular, then they're a lot more complicated. So I want to draw a picture and label some parts. One, we've talked about polygons in the past, so this is kind of a reminder of some of these things. So I'll do a pentagon here. So there's our regular pentagon. This point in the middle is the center. And if I connect the center to two vertices, this angle is the central angle. And that central angle is going to be important for what we do with polygons. So let me draw another pentagon, and we'll label some more parts. So we still have our center, and I'm going to draw a segment here that goes 90 degrees to one side. That segment is called the apothem. And that is going to be a very important part of our polygon. The segment that goes from the center to a vertex is called the radius. And we call it the radius because we put a circle around here with this at the center, and that would be the radius of the circle. So that's the radius we call that the radius of our polygon. Now, if we have a regular polygon, what do we know about each radius? What about their lengths? If this is a regular polygon, how does the length of this radius compare to the length of that radius? They're the same. So this would be an isosceles triangle. So I could draw in, if I drew in another radius here with dotted lines. This is an isosceles triangle. What does the segment that goes from the vertex of an isosceles triangle perpendicular to the base, what does it do to this angle? Bisects it. So this is half the central angle. What does the segment that goes from the vertex to the base of an isosceles triangle do to the base? It bisects the base. So this little piece of the triangle is half a side of the polygon. This little triangle that we're drawing here with the apothem, the radius, and half the side is very important when we're talking about the area of regular polygons. We'll use that little triangle a lot. So we have the apothem that goes from the center 90 degrees to one side. It cuts that side in half. The apothem cuts the central angle in half. And then we have this little triangle made by the radius, the apothem, and half the side. All right, who remembers how to find the measure of the central angle of a regular polygon? If I start here and I go all the way around, how many degrees have I gone? 360. How many sides do I have? 5. 360 divided by 5. So the central angle of any polygon, any regular polygon, is 360 degrees divided by the number of sides. That will be important because we'll need to find the measures of these central angles. So just a couple of things to think about as we're moving forward. This triangle that I've drawn in red here, we will end up using the Pythagorean theorem on that right triangle. We will end up using SOHCAHTOA on that right triangle, and we will end up using our rules for special right triangles on that right triangle, all having to do with areas of regular polygons. So all of those ideas come together in this little unit or this little piece about areas of regular polygons. So just keep that in mind as we go forward. All right, so there's our quick down and dirty review of polygons. So let's do an example of finding some angles in a polygon, and then we'll talk about how we find an area. So we'll stick with a pentagon. And we're going to say this is a regular pentagon. So our regular pentagon. And I'm going to draw in some pieces here. And I'm going to label angle 1, and this is a 90-degree angle. 2 and 3. And our problem says find measure of angle 1, measure of angle 2, measure of angle 3. All right, so which one can we find right away? I had heard a 3 and a 2, and I was thinking angle 1. What kind of angle is angle 1? It goes from the center, and the sides of the triangle go to 2 vertices. So what do we call that angle? What's that? One more time. A central angle. Angle 1 is a central angle. Goes from the center, and the sides of this triangle go to 2 vertices. So how do we find the measure of angle 1? (360) divided by 5, and that turns out to be 72 degrees. So angle 1 is 72 degrees. That was the easy one to find. Angle 2, now we're set for angle 2. What does this, if I draw this, what does angle 2, what does this segment do to this central angle? Bisects it. So angle 2 is half a central angle. So the measure of angle 2 is 72 degrees divided by 2, which is 36 degrees. And then we're set for angle 3. How do we find angle 3 now? So all the angles have to add up to 180 degrees. So I add 36 and 90. 36 plus 90 is 126. 180 minus 126 is 54 degrees. So the measure of angle 3 is 54 degrees. So being able to figure out the central angle, draw this little triangle, figure out half the central angle, and figure out this angle down here in this triangle. And I'm going to highlight this little triangle that I'm highlighting in red. Being able to find those angles in that little triangle is going to be very important. So we'll need to be able to do this to find our areas of regular polygons. All right, guys, electronics, let's put them away, please. All right, so let's talk about our area formula. Any questions about this example? Just finding angles. The key is our central angle and drawing this little little triangle. All right, our area. Area of a regular polygon. So I'm going to draw a hexagon this time, just to have a different shape here. And what we're going to do, just so we know where this formula is coming from, it's not just something that we made up out of thin air. I'm going to draw in a central angle, 2 radii from the center. I can divide this hexagon into triangles. So I could draw in radii to each vertex, and I would divide it into triangles. What's the area of a triangle? Base times height divided by 2. Well, here is the base of the triangle. Let me draw in the height. There's the height. What part of the polygon is the height of this triangle? From the center, perpendicular to one side. What do we call that piece? That's the apothem. So the area of this triangle is one side of the polygon times the apothem divided by 2. For a hexagon, we would do that 6 times. So we would have 6 sides that we're adding together. That's the perimeter of the polygon. So our formula comes from taking the area of this triangle and adding it together for however many sides of the polygon we have. So we know where the area comes from. So our area is 1/2 the apothem times the perimeter and P is the perimeter. What I would suggest that you draw in the little circle where it says regular polygon, I would suggest you sketch a little inside the circle, a little polygon, and label your apothem even if you just say A. And you might want to, so you know what the apothem of your polygon is. So I would suggest you draw that little picture in the circle so you know what the apothem is. And P is the perimeter. So the mistake that students make often is they confuse the apothem and the radius. You want to make sure you're getting the right thing there. Yes? The perimeter of the polygon. And how do we find the perimeter of any shape? Add up all the sides. And that's on your graphic organizer also. Perimeter, add up all your sides. So that's at the 9 o'clock position on your graphic organizer. So to find the perimeter, we just add up all the sides. The apothem from the center, 90 degrees to one side. And we plug our numbers into our formula. And our units are always units squared. Square units. Square inches, square centimeters, square miles, square feet, something like that. All right, questions on our formula? All right, let's do a couple of examples calculating the area. Okay, here is our shape. We'll do a pentagon. So this is like our opener. Find the area. That's 12 centimeters. And this is 8 centimeters. So we know that our area is 1/2 the apothem times the perimeter. Do we have the apothem here? Is that segment the apothem? Yes. From the center, 90 degrees to one side. So our apothem equals 8. Our perimeter, how do we find our perimeter? Add up all the sides. So I have 12 sides times, or 12 centimeters times 5 sides, and I get 60 centimeters. So the perimeter is 60 centimeters. 12 plus 12 plus 12 plus 12 plus 12. Get 60 centimeters. So I just plug those numbers into my formula. The area equals 1/2 8 times 60. 1/2 is the same as dividing by 2. I could multiply these together and divide by 2. I could divide one of them by 2 and then multiply. Doesn't matter what order. When I calculate this out, half of 8 is 4. 4 times 60 is 240. So the area would be 240 square centimeters. Questions on that example? All right, let's look at another one. And this one's going to be a little trickier. All right, same thing. Find the area. Uh, 11.88. All right, so we have one side, so we can figure out the area or the perimeter. We know that area equals 1/2 the apothem times the perimeter. Our perimeter is 5 times 14. 5 times 14 is 70. Do we have the apothem here? Guys? Do we have the apothem? No, what do we have? We have the radius. How can we find the apothem? Draw in the right triangle. This one is not a 30, 60, 90 triangle, but we can do something else.
Oh, yes.
What does this segment do to this side of the polygon? Cuts it in half. So what is this little piece? 7. So now I have a little right triangle. I have two sides and I need to find the apothem. What always works on a right triangle? A squared plus b squared equals c squared. I have two sides. That's our look for the Pythagorean theorem. So I know that a squared plus 7 squared equals 11.88 squared. So I can find a using the Pythagorean theorem. So a squared plus 49. 11 squared is 141.13. Subtract 49. I get a squared equals 92.13. Find a, I take the square root. And I finally get a equals 9.6. And I would plug that into my formula. The area equals 1/2 9.6 times the perimeter times 70. And I would calculate that out, yes. We could have done that, and we'll talk about doing that in another section. Yes, so we will end up doing that as well. If they didn't tell us the side length, we would be able to figure out the sides of the triangle using SOHCAHTOA. So even if we have one less piece of information, we'll still be able to do it. That's kind of nice thing. So now I'll calculate this out. I didn't calculate it out. Anybody have a calculator? Calculate this out. Point. Even? Oh, okay. So our area is 336 units squared. So sometimes we have to use the Pythagorean theorem. We can always use the Pythagorean theorem on that little triangle. All right, are we good with polygons so far? Okay, the next thing we need to talk about is how we find special right triangles in polygons. So special triangles in polygons. So we're going to do 3. The first one is squared. And what I'm going to suggest for these is I'm going to draw a little picture here. I would suggest you draw these little pictures on your graphic organizer where it says regular polygon. You have little lines coming out that says square, hexagon, and other. So I'm going to draw a couple of pictures. You should draw these pictures under the line that says square. So I'm going to draw 2 squares. There's 1. There's 2. There's the center of my square. This is the center. There's the radius. And there's the apothem. This triangle is a 45, 45, 90 triangle. And this length is half a side. This cuts the side in half. So we end up with a 45, 45, 90 triangle when we draw the radius and the apothem of a square. And we can use our rules for 45, 45, 90 triangles to find side lengths. The other way we get a special right triangle in a square is by dividing it straight in half. There's my center. That is a 45, 45, 90 triangle. So sometimes we'll need to use this information to find pieces of a square. So squares give us 45, 45, 90 triangles. I can use the rules for 45, 45, 90 triangles to find sides, legs, and hypotenuses of these triangles. All right, the next one I want to do, we're going to skip down to where it says Other. We're going to do an equilateral triangle. And I'll just go ahead and go to a new page. So for an equilateral triangle, I'm going to draw two equilateral triangles. What do we mean when we're saying that the triangle is equilateral? All the sides are the same. What does that make all the angles inside the triangle? All the angles are the same. Three angles that are equal that add up to 180. 60 degrees. So we end up with a 60-degree angle inside an equilateral triangle. So what special triangles do you think we're going to be talking about now? We end up with 30, 60, 90s. So here's my center. When I draw the radius and the apothem, I end up with a 30, 60, 90 triangle. And this is half a side. So when I draw the radius and the apothem of an equilateral triangle, I end up with a 30, 60, 90 triangle. And I can use the rules for 30, 60, 90 triangles to find pieces of that triangle. The other thing I'm going to do with an equilateral triangle is divide it straight in half. We decided that's a 60-degree angle, and that's a 30-degree angle. And this is half a side. So we end up with a 30, 60, 90 triangle when we divide an equilateral triangle in half, or when we draw the radius and the apothem. And we can use these 30, 60, 90 triangles in our rules for 30, 60, 90 triangles to solve for missing pieces. All right, the last one is a hexagon. And I always say hexagons are special. Hexagons are special. And we just need one picture of a hexagon. And let me draw that. Let me draw that one a little bigger. All right, here's our center. Here's our radius. What would be the central angle of a hexagon? 360 divided by 6, which is, what is it? 60. And when I cut it in half with the apothem, I get a 30-degree angle. There's a 30-degree angle, there's my 90-degree angle, and there's my 60-degree angle. And this side of the triangle is half a side. So inside a hexagon, I have a 30, 60, 90 triangle. And I can use my rules for 30, 60, 90 triangles to find missing pieces. So you should have these little pictures with your 30, 60, 90 triangles drawn in there around that circle in your graphic organism. Squares, triangles, hexagons. You end up with special right triangles. All right, questions on our special right triangles? Okay, let's do a couple of examples using these special right triangles, and then we'll be done. Using these special right triangles is really a key thing to understand in this section and really in this chapter, because it comes up a lot. And these are the kinds of questions, especially with the hexagons and the equilateral triangles, kinds of questions they like to ask on standardized tests, like the new PARC test that we're going to come up with, like the ACT, like the SAT. They like to see if you remember these things. All right. Find the area. We're saying this is a regular hexagon. And that's all we have, is one side, 10 inches. And we want to find the area. So what are we going to do here? Draw the center. Get out our ruler and start measuring. What are we going to do with the center now? Draw in. We need our apothem. We know that the area is 1/2 the apothem times the perimeter. Well, the perimeter is easy. The perimeter is 10 times 6, or 60 inches. That's easy. We don't have the apothem. We don't know it, so let's draw it in. Here's my apothem. What's that? We know the central angle. So here's where we want to draw. We draw the apothem. We want to draw that little triangle inside our hexagon. So I'm going to draw the radius also. There's my apothem. Cuts this side in half, right? So what's this side of the triangle? 5. This is a 60-degree angle. This is a 30-degree angle. Here's my apothem. Is 5 the short, the long, or the hypotenuse of this 30, 60, 90 triangle? Which side is it? The short side. How do I go from the short side to the long side? Multiply by the square root of 3. If it helps, you can always redraw this triangle outside of your hexagon. And I'm going to draw that 5, call that A. You can just redraw it. And we know this is the short, this is the long. We want to go from the short to the long. We know we have to multiply by the square root of 3. So the apothem is 5 times the square root of 3. And now I can plug my numbers into my formula. The area, and that would be in inches. The area equals 1/2 5 square root 3 times 60. 5 times 60 is 300. I can multiply outside the square root. 5 times 60 is 300. Half of 300 is 150. So I get 150 square root of 3 inches squared. So for a hexagon, all I need to know is the side length, and I can find the area by using special right triangle. Are we good on that example? Okay, let's look at another one. Same kind of thing. Find the area. I don't want that shape. I want a different shape. There we go. This time we have an equilateral triangle. Equilateral triangle, and that's 14. Okay, what are we going to do here? Draw. So for an equilateral triangle, we can draw the center. I think it's a little easier just to cut it in half. The area of a triangle is what? How do we find the area of a triangle? Base times height divided by 2. Well, here's the base. The base is 14. What does this segment do to this side of the triangle? Cuts it in half, so that little piece is 7. This is a 30, 60, 90 triangle. All right, we have a 30, 60, 90 triangle. If it helps you, redraw this triangle out, or redraw the 30, 60, 90 triangle outside. Do we have the short side, the long side, or the hypotenuse here? Short side. We need to find the height to go from the short side to the long side. Is the long side longer or shorter? Longer, so we have to multiply. We already know the hypotenuse, right? The hypotenuse is 14. So what do we do to get to the height? Multiply by the square root of 3. So the height is 7 square root 3. The area is the base, 14, times 7 square root 3, divided by 2. And to find this, to calculate this, I'm just going to divide this 14 by 2. 14 divided by 2 is 7. Multiply outside the square root. 7 times 7 is 49. 49 square root 3 units squared. The base of the entire triangle is 14. We're trying to find the area of the big triangle. So the base, this whole side is the base. That base is 14. Because it's an equilateral triangle. So that's an easy mistake to make on this. Is the students will want to use the 7 as the base. Well, the 7 is only half the side of the triangle. We want to use the entire base, the base of the entire big triangle, to find our area. So we end up with 49 to the square root of 3 units squared. All right, one last example. Hexagon again. Hexagons are special. Find the area. And this time, here's the information we have. This is a regular hexagon, even if it doesn't look like it. And I want to draw a different segment. Let me do this. I don't want that. I want this. All right, we know that our area is 1/2 the apothem times the perimeter. Well, now we have the apothem. The apothem is 4 square root 3. We need to figure out the perimeter. So in order to find the perimeter, we have to find our side length. How can we find our side length? So you're exactly right. You're just you're a couple of steps ahead of us. So let's go step by step. What if we weren't sure what to do? Draw in your little triangle. So I'm going to draw this triangle. My 30, 60, 90 triangle inside a regular hexagon. There's my 60 degree. There's my 30 degree angle. This piece of the 30, 60, 90 triangle is half the side length. And if it helps you, you can draw it outside the hexagon, draw it a little bigger. And that's our 60-degree angle, and that's our 30-degree angle. This is our 90-degree angle. Is 4 square root 3 the short, the long, or the hypotenuse of this triangle? Long side, we want to find the short side here. So to go from the long to the short, Olivia says we divide by the square root of 3. So the apothem, or the short side, is 4 square root 3 divided by square root 3. And what does that give us? Anything divided by itself is 1. Those cancel, right? We just end up with 4. So this piece is 4. So the whole side is 8. So our perimeter is 6 times 8 equals 48. And our area is 1/2 4 square root 3, our apothem, times 48. Half 4 is 2. 2 times 48, I'm multiplying outside the square root. Half 4 is 2. 2 times 48 is 96. 96 square root 3 units squared. And that would be my exact number.
Where did you get the 6 from?
The six sides. The perimeter, we need 8, and we have 6 of those sides, so we have to add up 6 of those sides, since we have a hexagon. All right. Questions on that example? Using these special right triangles with hexagons, with equilateral triangles, really one of the key things from this really the key thing from this section, other than this formula, and really one of the key things of the unit is that you understand that those special right triangles are inside those shapes. All right, let me put up the homework, and then we'll go over the homework from before. Whoops, that's pre-calculus.